Now we will argue that the simplex algorithm is correct, giving us a basic feasible solution for bounded linear programs and reporting that unbounded ones are unbounded. Let's consider the bounded case first. First, we recognize that at each step we make some progress, usually improving the objective value. We have to be careful here in the case of degenerate basic solutions. Going back to the algorithm, remember that we picked a new column to go into the basis because it had a positive corresponding value in RD, and hence increasing it increased the objective value. The trouble is that if the current basic solution is degenerate, that is to say, that V has a 0 entry, it's possible that we won't get to move in this direction at all. The nightmare scenario is that we end up in some kind of cycle. There are two ways of coping with this challenge. One is to perturb the constraints slightly. The other is to give preference to lower indexed columns for both entering and leaving the basis. This is known as Bland's rule. In either case, we can be assured of making some progress in each step, but I'll put an asterisk here because the notion is a little tricky. Clearly, we have a finite number of steps because there are only n choose m possible bases, and because we make progress, we don't cycle among them. Now we just need to make sure that we don't stop too early. There are two possible ways the algorithm can terminate, either because u is non-positive or because rd is. Let's consider the termination because of u first. This turns out to be pretty trivial. If u is non-positive, then we get to keep going in the direction of dq here as much as we want, increasing the objective value the whole way. So clearly the problem is unbounded. And of course that can't happen because we've assumed that the linear program is bounded. Let's consider what happens when we terminate on the RD condition then. We'll let x star be an optimal feasible solution that's not necessarily basic, and we'll let x be a basic suboptimal solution. Well, using the basis for this basic suboptimal solution, I can write xb star in these terms here. This just comes from the equality constraint and the feasibility of x star. Substituting this expression back into the objective function gives me this result here. This expression here is the same RD that we obtained in the simplex method. And because x is suboptimal, we then have this strict inequality here. Because x is basic and b is its basis, however, xd is 0, so we can simply annihilate this term. Also, xd star is non-negative, so for the strict inequality to hold, at least one entry of RD must be positive. Hence, if there's a better solution, the simplex algorithm won't terminate. That wraps up the case where the program is bounded. How about when it's unbounded? Well, by the same argument just given, we won't hit the case where RD is non-positive. And the algorithm can't run forever because it avoids cycling, and thus can only visit each of the n choose m bases once. The only remaining possibility is that u will be non-positive at some point, and will report that the problem is unbounded, which indeed it is.